Ever wondered why computer science students should have a firm grasp of the limit theorem in probability distribution 2? Imagine harnessing the power of probability to predict the behavior of complex algorithms, machine learning models, and statistical analyses. This theorem, a cornerstone of probability distributions, offers profound insights into the stability and predictability of statistical outcomes, even as sample sizes approach infinity. So, are you ready? Brace yourself for a fascinating journey into the world of probability distributions. And the limit theorem, a cornerstone concept in probability theory, offers intriguing insights into the behavior of random variables. This theorem is a key player in the world of probability distributions, shedding light on how random variables behave as the sample size approaches infinity. Now, there are two key forms of the limit theorem that we need to talk about. First, we have the central limit theorem. It suggests that the sum or average of a large number of independent and identically distributed random variables tends towards a normal distribution, no matter what their original distribution was. Quite fascinating, isn't it? Next, we have the law of large numbers. It asserts that as we increase the sample size, the sample mean converges towards the population mean, giving us a more accurate reflection of the true characteristics of the population. These forms of the limit theorem provide the foundational knowledge that shapes various applications in computer science. From Monte Carlo simulations to machine learning models and complex algorithms, the limit theorem plays a pivotal role. Its magic lies in its versatility. Take Monte Carlo simulations, for instance, a staple in computer science for modeling complex systems with random variables. Here, the central limit theorem is the star, enabling these simulations to yield accurate approximations of real-world phenomena. Then we have machine learning, where the limit theorem aids in assessing model performance and estimating confidence intervals for predictions. It's like a trusty guide, facilitating the interpretation of statistical metrics and enhancing the reliability of predictive models. And let's not forget algorithm design. Algorithms often rely on probabilistic analyses. The limit theorem acts as a trusty compass, guiding developers to design algorithms with robust performance guarantees, even in stochastic environments. Imagine a software engineer optimizing a search algorithm. By applying the limit theorem, they can confidently estimate the algorithm's average execution time and assess its scalability. Thus, understanding the limit theorem empowers computer science students to craft efficient algorithms, build reliable machine learning models, and tackle computational challenges with confidence. In the realm of computer science, the importance of understanding the limit theorem in probability distribution 2 cannot be overstated. It's key in comprehending random variables' behavior and making informed decisions in algorithm design, machine learning, and statistical analysis. Remember, it forms the backbone of Monte Carlo simulations, aids in assessing machine learning model performance, and enables robust algorithm designs. Mastering this theorem equips students with the essential tools for tackling real-world challenges in computational problem-solving.